Okay, so today we'll be looking at a variety of angles we'll be using in trigonometry. I call this rotation angles. So there's like a lot of vocabulary in this lesson. Other than that, I think the mathematics is really simple. So the first type of angle that we're defining is which one? Can you guys tell me? What's the definition that we're looking at? We're defining what term here? It's a little bit tricky. Think about it. What term is being defined?
Standard position.
So Gosh says standard position. Do you guys agree? Does that seem to be what that definition is defining? I think so. Yes. So the first type of angle we're going to look at is what it's called to be in, what it is to be in standard position. Because in trigonometry, in the vast majority of cases, your angles end up being in standard position when you're considering them. Okay? So something in standard position means that the angle, opening however much, it could be an acute angle or an obtuse angle. It doesn't have to be an angle in a triangle. It can be much more, like we're going to look at 990 degrees here in a second. But any angle in trigonometry usually is in standard position. So what that means is that one of its sides, one of the rays in the angle, because of course an angle is two rays, right? Two things that start somewhere and keep going. That's what a ray is. One ray is the positive x-axis. That's what it means to be in standard position. So in standard position, this is the first side of the angle, if that makes sense. And we call this side the initial side. Bless you. Which should make sense because it's like the beginning side. That's what initial means, right? Initially is starting off. So that's the first side, and of course the terminal side, the ending side of the angle, can go in all kinds of different places. It could be in quadrant 1 for a nice acute angle. It could be in quadrant 2 for kind of obtuse angles you guys have seen, like 150 degrees and so forth. But it could also be in quadrant 3, more than 180 degrees. It could be all the way over here, so you're going all the way into quadrant 4, or it could be multiple times around. So that terminal side can land all kinds of places. Let's just draw a nice obtuse angle for this example. So we'll call this the terminal side. And this angle right here that I'm talking about, what do you guys think? I guess it's a tough call, but in basic trigonometry, in the regular standard position angle system, we call that positive rotation. Okay, so this is a positive angle, this is positive rotation. So it's going to be a positive number of degrees or radians that we're going to start looking at next week. If you decide to rotate the opposite way, clockwise from that beginning x-axis, you're going to get a negative angle. So if you went something like this, and you went that much to get to this terminal side, that would be negative rotation. So you'd have a negative number of degrees or radians. So can you have negative angles? Yes. All right. Now, there are other coordinate systems besides standard position. For instance, pilots often use this as their standard starting spot, the vertical one. And you know, different other scientists and different other people use other standard positions. But this is the one you're pretty much always going to see. Okay? You'll see variations once in a great while. Print out this year. All right, so I wanted to ask you guys, can you help me with what are the cardinal edges of this? If you're just going around once, you start with 0 degrees. How many degrees are here if you go that far? Positive 90 degrees, and if you keep going in positive rotation, 180 degrees, and down here then would be plus 9 would be 27, so 270, and all the way around in a circle is 360 degrees. There's no reason to say you have to stop there, but let's just get those as landmarks, okay? So let's draw these three angles in standard position. So I'm going to ask you guys, let's see, Mr. Goodwin, can you tell me 320 degrees? What quadrant is the terminal side going to land in?
Most likely be in the quadrant.
Which one?
Fourth.
The fourth, yes. That sounds good, right? Because it's going to be almost a 360, but not quite. Somewhere like right here. So it's going to be like that. That's what that angle looks like. Nothing difficult, right?
You just kind of draw like a rough sketch of where.
Yeah, it's just a rough sketch, exactly. I mean, we're going to be more precise when we need to be, Mr. Hildreth. Good question. Negative 110 degrees. What do you guys think? What quadrant? Mr. Garner says third quadrant. You guys agree? 1, 2, 3. Except he's going this way, right? It's 20 degrees past negative 90. So, yep, that's that angle. 990. We might have to count for a while now, right? Let's try not to use our calculator though. We want to get used to counting like this. So 180, let's think 18, then 36. What's another 18 from 36? Or, you know, if you like snowboarding or something like that, that's going to be helpful now because what's 2 times around? It's a 720. So it's more than 2 times around. What's 3 times around? No one does that in snowboarding hardly unless they're really awesome. That's 1080. So 1080 is getting close, right? So this is almost 3 times around, except 1080 would be all the way back to here. So we should go back 90 from 1080. What would that be?
990.
Oh, it's right there. So you should try counting. Use your snowboarding vernacular. You know, your experience that you developed and stuff like that. I know we've all watched the X Games and stuff. If not, I guess you can count with your numbers. But so we're going to go around. Once is 360. Twice is 720. 3 times would be 1080. We decided we were going to stop here. I'm sorry, my circle is not centered. It should be. Okay? Why don't you guys try those other couple examples? Take 1 minute in the handout and complete the other 2 that I have on that one. Okay, so a second kind of angle we'll be working with in trigonometry is what? What term's being defined here? What it means to be coterminal, those kind of angles, that variety. So we're defining coterminal angles here. So I wanted to think about the coterminal angles that we'd get for theta. This theta, not just any old theta, this one, 65 degrees. So if they have the same terminal side, well, we should probably figure out where that terminal side is first, right? So what quadrant would the end side for 65 degrees be in? The first quadrant, right? Something like this. There it is. So somebody give me another angle that is coterminal with theta.
Yeah, 360.
Jacob says add 360. So what's another one? Let's call it theta sub c for coterminal. So let's get C1, the first coterminal angle.
425.
425 is it? So you can see that Mr. Garner said he's going to add 360. Why did he add 360? Why didn't he add 180 or 720 or something like that? Because he just started here and went all the way around from there and got back to the same spot. Does that make sense? You could add 720 because that would just be going around twice. So that'd be another coterminal angle. If you add another 360, what do you get? 785? Is that right? If you add 360 more?
Yeah.
I think so. Could I add another 360 and get back to the same spot?
Yeah.
You could add
Sure. How many times could I do that? An infinite amount of times. And I don't just have to go forwards, I could also go backwards and get like the first back this way would be another one. You can call it whatever you like. I called it coterminal 3. So 65 minus 360 is negative 295. I think Mr. Garner is correct. And we can keep going backwards too, right? So how many coterminal angles are there for any angle? An infinite amount. Let's make a note of that. There are always an infinite amount of these. Now, that might not seem like a big deal to you right now, but we're going to need to learn how to count and describe an infinite set in order to work with trigonometry, and it's all coming from this fact right here. In fact, a whole bunch of stuff about trigonometry is all going to go back to going around and around and around, repeated. Okay, so it all starts right here. So what do you guys think for 410 degrees? Let me ask, can somebody tell me a positive coterminal angle to that without even drawing it this time? You guys have played already. Miss Reed? What?
770.
770. You guys like 770? That'd be a positive coterminal angle, okay. So what's this guy's name again?
E.
That's theta. This guy's name is phi, or phi. So phi1 coterminal, Miss Reed told us 770. Can somebody give me another positive one? Mr. Ross?
1030.
1030, is that right? If you add another one? Now the directions might ask you to just give any two coterminal angles. They might say, give me a positive and a negative coterminal angle. What's a negative coterminal angle with this one? Negative 310. How is Mr. Crane getting that? I think he went 410 minus 2 times 360, or did you go minus 720?
Oh, minus 360 minus 360.
Yeah, so he did 360, subtracted it twice to get a negative one. And you came up with what?
Negative 310.
Yeah, I'm bad with numbers, that makes sense.
You should do negative 1,000.
Okay, and we could of course draw all these coterminal angles, but they're all going to have the same side, so it's going to be pretty boring, lots of circly stuff. Okay? So there you go, coterminal angles. Why don't you guys try the couple on your sheet? So our last type of angle we're going to investigate today at least, and that's one of the other big three pretty much, is what's called a reference angle. This is probably the most important one. I don't know, coterminal is pretty important in concept. This one's important mechanically when we start doing the unit circle next week, which is what people who struggle in more advanced math generally tend to struggle with, but we're not going to, I'm hoping. So a reference angle is the positive angle formed by looking at the terminal side and the x-axis. This has a lot to do with how you take sines and cosines and tangents in the other quadrants. Because of course we're not going to just have angles limited to quadrant 1 like you've seen so far. You guys know what I mean? With like your sine of 30 degrees, your cosine of 45 degrees, those ones. They're going to go into other quadrants most of the time. Well, maybe not most of the time, but a lot of the time. And you're going to need to be able to deal with that. Reference angles are the key to dealing with that, okay? So let's think about 150 degrees and find its reference angle. We'll try to follow the definition, okay? So you guys, can you help me draw this? Let's try to read from the definition. Help me out. So 150 degrees, first of all. Mr. Gehrig, what quadrant's that in?
That would be in so if you're going that way, it would be
Second, because we're going positive.
yeah.
Okay, so it's over here, right? So there's 150 degrees. What I want to know is, for 150 degrees, what's its reference angle? There's only one. Where should I draw from this terminal side to form its reference angle? I should draw from that terminal side to the x-axis. This thing is its terminal angle. Now how do you think you find that?
You just subtract 180.
Use common sense. What's here?
30.
180, so 180 minus 150 is 30. So the reference angle here is 30 degrees. It's that simple. It's easy to mess this up though, and I have had students who've been successful in trigonometry who did things a really weird way in my first year at Rye, but man, it's hard to make mistakes and then somehow get the right answer. So I wouldn't recommend doing it that way, so I'll give you a little tip in a second. Negative 105 degrees, what quadrant's that going to be in? Miss Miller, what do you think? Here?
Yeah, right there.
Right there about, right? Just a little bit past negative 90? Okay. So that's negative 105. That's beta. But what's beta's reference angle? Where should I draw? Should I draw like this?
No, drop towards one.
Should I draw like this?
No.
Kind of, but I went too far, right? It's just this piece trapped between the angle and the x-axis. It's always a vertical type of trapping for that reference angle, okay? So how much is this going to be? Difference between 180 and 105 is 75. Now, I know you guys are asking yourselves, is this negative or positive 75? What's the definition say? It says positive. Reference angles are always positive. They're just the amount of space in absolute value, you might say, between where your terminal side is and the x-axis. Okay? That's it. So 325. Let's see. Mr. Calgill, can you tell me which quadrant is that going to be in?
It's gonna be in the fourth.
Yep. So we'll go like this. Somewhere over there. There's 325. That whole thing. So what do we think? Mr. Willis, reference angle?
Right there. Yeah.
There, okay, he's pointing right. And what have you got for it?
That'd be
Somebody help him? What should he be subtracting here? Mr. Jensen, what do you think?
You should subtract 360.
Yeah, you could go 360 minus
Right.
325, which would be
Until you get, it's 35.
35. You could also go from 180 and think about what you have to add. That'd probably be a little harder, but that's also another option, right? Or you could go from 270. Don't forget this one's 270.
What about 90?
You could go from 90. You're just an untraditional guy, gosh. But yes, you could do that if that works for you. Okay, so if you're watching the video right now, I'd pause it and find those reference angles for your worksheet. So, before we go on and do one last type of problem in this rotation angles section, let me give you a tip for reference angles. Reference angles should always look like one of four things, and there's a nice shape you can remember, and if your reference angle doesn't look like part of that shape, you're wrong. Okay? So, what shape would it be? It's always to the x-axis, right? So in quadrant 1, if you have an angle like that, the reference angle is this angle. It means you're going to get a reference triangle that looks like that triangle. Over here, if you have the terminal side, which way do you draw? Do you draw horizontally or vertically? Look at your other examples if you're not sure. It's vertically. It's down to the x-axis. So that's the shape of triangle you'd get for that reference angle. Okay? Over here, the terminal side landed somewhere like that. You'd draw vertically again. Over here, you draw vertically again. What shape does this look like? Bow tie. So if your triangle in trigonometry, you're trying to do a calculation next week into the future, and it doesn't look like your reference triangle you're using doesn't look like part of a bow tie, you're probably not drawing it correctly. In fact, it's like 90% chance you're not doing the problem correctly. Does that make sense? So bow tie is your Bible. All right, be snazzy. So one last type of question. This one says we've got a point, it lands on an angle. This is the notation in geometry for angle, by the way, so you know something from geometry. So we want to find all 6 trig ratios, the ones we've been working with. So what quadrants does this point land in? If it was in quadrant 1, this would be boring. We already know how to find the trig ratios. But this is in quadrant 2, isn't it? Let's plot it. So on a problem like this, you just, of course, want to start by plotting it. -2, 7. So that point is right here. There's P. It says P is on the terminal side of an angle, so I'm going to put an angle through it. That's like this angle, right? But the great thing about what we've been learning is, if you create the reference angle for that blue guy, it has the same value for all 6 trig ratios as just the triangle. And we already know how to do this for a triangle. Okay, all 6 trig ratios will be the same for the blue guy as the little triangle you create with its reference angle. So let's draw its reference angle. Where should I draw?
Down.
I should draw down. Oh, and mine is kind of bent. We're going to pretend that this is right here. Okay? So here's the reference triangle. Let's give it a name like theta. And there we go. So we're going to label the sides of it. Let's say this side is 7 and this side is how long? 2. But it's not just 2 because 2 would be over there. So we need to include the negative to say that it's in the second quadrant. Does that make sense? That's the reason you include the negatives on these. When you are down here, both x and y are going to be negative. When you're over here, what's going to be negative? Only the y value. The x will be positive because it's still going that way. Okay, so make sure you label with negatives included. We also need the hypotenuse of this right triangle. We use Pythagoras. So we'll go 7 squared plus -2 squared equals c squared. 49 plus 4, so c is going to be the square root of 53. I don't think that reduces. If it reduces, reduce it. You know, if you can pull square numbers out of it, reduce that square root. So let's go ahead and label that as well, square root of 54. And now it should be no problem at all to figure out the 6 trig ratios.
53.
Can I not count again?
Yeah, you put the road in.
And I said 54 too. 53, sorry. Okay, so sine. Let's see, Miss Richardson, can you tell me what is the sine of that triangle for theta?
It would be 750 square root.
Yep. 7 over the square root of 53, if you can read my 53, sorry. I don't like 53 for some reason. Miss Russell, what do you think for cosine of theta? What's the cosine of this angle? Yep. Tangent. Let's see, Mr. Stosic, can you give me tangent?
7 over -2.
Opposite adjacent, you got it. Would be -3.5, right? And then for cosecant of theta, what am I going to have, Mr. Garner?
Square root of 53.
And Mr. Lee, what are we going to get for, what's the next one, by the way?
Secant.
And it's going to be, what are you going to get? Root. Yeah. And cotangent, I'll do. And if we were going to clean these answers up and make them better, which ones would need to be cleaned up and fixed? Mr. Valdez.
Negative, 7 over
Which one?
-2. 7 over -2.
This one?
Yeah.
Well, we could say -3.5. I agree, Miss Russell. You have a different idea?
Sine and cosine.
Yeah, sine and cosine are the main ones because they are divided by a square root. These could be rationalized. A better answer for this is going to be 7 root 53 over 53. And a better answer here is this. Both good. Okay, it's all about recognition. That's why I'm saying it's a better answer. Okay, I think that's it.